Okay, so good evening, everyone. I'm Calvin Joseph, and today I'll be conducting your week 5 problem solving and doubt clearing session for the course Control and Tuning Methods in Switch-Mode Power Converters. So today we'll be discussing about why do we require to do modeling. Like Sir has talked extensively in this week about different modeling techniques, and from those modeling techniques, what can we do, what can we find out, etc. That those we will check today. Okay, what are the states considered which Sir has used in his modeling? Like if he has done the modeling for boost converter, buck boost converter, and all that, Sir has considered the inductor current and the capacitor voltage as the states. So that why is it there? Then we will do a method known as state space averaging, how it is very useful for us to get a model from that. Then circuit averaging is another method. Then we will look into what is the DC equivalent model. And then we will solve some sums. Okay. So this is week 5. So we are talking about modeling. So can you tell what is the need for modeling? Why do we need modeling? What is the purpose of modeling? Or without modeling, can we do our work? Okay. So modeling is required because we want to understand our plan. We want to know our system. Or else we cannot, because our system is costly, right? It is costly. It is not like a boost converter. Make a boost converter. You have to make a PCB. You have to get the components. You have to mount the components, and all that. It takes a lot of work. And after doing all that work, we don't run the system properly. Or we assume the system can do this, but it doesn't do it. It is not capable of doing it. So there is an issue. Like we need to have a model of the system such that if we know we give these inputs, my system will behave like this. If I give these inputs over here, it will behave like this. If I do this, give this extra input over here, it will become unbounded, it will become unstable, or it may collapse, all that. Okay, so that's why we need a model of our system. Okay, so that we'll have a idea of the mathematical behavior of the system. Secondly, we don't want to just keep changing. Like I will change this value, change that value, change another value, constantly go up and down, up and down, up and down to get some good response or good behavior. We want to have a mathematical analysis or something which says that this value through math has come out to be this, and this is the optimum value. This value, through this you can get your desired performance, etc. We want to have that guarantee, and that guarantee your mathematical model will give. Okay, so we get what is known as a mathematical model of the system. So let us say a buck converter or a boost converter. Is it a linear system? What do you think? Is it a linear system or non-linear system?
A non-linear system.
Okay. Why is it a non-linear system? What is the cause of the non-linearity?
Because of that switching action.
Yes. So these DC to DC converters are a non-linear system because there is a switching. That is, you have a gate signal Q. This is how it will go like this, like this, like this. Okay, this is how your gate signal goes. Your inductor current will follow like this. Will go like this, like this, like this, like this. and sorry, your output voltage is like this. In the case of a boost converter, it rises. When it's on, it falls. Then it rises again. Then it falls like this. Okay, this is your output voltage. And there'll be these points. Okay, it will not be smooth. There will be some jump, which is known as the jump due to the ESR jump. Okay, these are due to the ESR jump. So it is because you have one system here and you have your second system here. So you are combining two systems. Okay, your system one, that is when Q equal to 1, that's not system, let us say your circuit A, that circuit is a linear system. Okay, it's a linear system. Your when Q equal to 0, your circuit B, that also is a linear system. But because you're switching, you're going from when the inductor is, when the main switch is on to the time when the main switch is off. Because of that switching behavior, that's why the overall system is a non-linear system. Okay. Next, if you see the inductor current, like there's a property of the inductor current that it will not change its value abruptly, like the inductor's behavior. When we learned inductor first, at least that's what I was taught, was the inductor will try to resist any change in the current flowing through it. Okay, so that means your inductor current cannot be like this and cannot directly go like this and go like this. Inductor current cannot change abruptly. It is continuous, it is smooth. Okay, they are continuous and smooth. So what quantities are continuous and smooth, those can be used in our averaging, in our modeling, etc. That's why in the modeling, what do? We consider the inductor current and we consider the voltage across the capacitor. These are our states because they are continuous. They do not change abruptly all of a sudden. But this output voltage of your boost converter, that will change because it has these transitions. It has what is known as the, due to the ESR of the capacitor, it has some jumps. ESR jumps are there. That is why you cannot take the output voltage as your state. You take the voltage across the capacitor as a state, and you take the inductor current as a state. Okay. Any doubts still here?
No, sir.
Okay. So that's one part. So today we'll be focusing a lot about the boost converter. So one question is there completely about that. So now we have discussed what states are continuous. Then we have what is known as state space averaging. State space averaging is, in control systems, which you guys should have studied, you would have what? X dot is equal to AX plus BU. So this X, they are your states. Okay. Your U is your input. Okay. Your A is your system matrix. And B is your input matrix. Okay. So we will be using matrices a lot. So it's good if you are well versed with them. So what happens is, in your circuit A, we will have X dot is equal to A1X plus B1 in the case of these DC-DC converters. And your circuit B will be X dot is equal to A2X plus B2 Vn. Okay, so you observe that this is linear time invariant. This also is linear time invariant. But because of the switching between these two systems, overall system is non-linear. Okay. So in circuit averaging, what we do is we will average the system over the time period. And then after that, we can give, a perturbation, and we'll do perturbation and linearization, etc. Okay. This is done. So, has anyone worked on the BJT circuits? When you do BJT circuits, what do you do? What are the steps you follow? Can anyone tell me?
We will do the DC analysis and AC analysis.
Yeah. So first you will do DC biasing. Like today only afternoon I had a lab. So like I'm a teaching assistant. There's a professor, and then some teaching assistants are there. So we will guide the second year BTech students in the lab. Okay, so they have this BJT circuits they have to do. They use the NPN, PNP transistors, everything. So, like the way I prefer the students doing is they should first check the DC biasing. That is, they have, let us say, your common emitter amplifier. They have something like this. Okay, this is your RC, RE. This is just a little bit off topic, but I'm just letting you know. This is your VCC. So this is your R1, R2, etc. Okay. So in the actual entire circuit, what do you have? They have a capacitor here. They have this decoupling capacitor over here. So over here, they apply the sine wave input, and over here, they view the output. Okay. So this is the input capacitor. This is some bias capacitor, etc. For restoring the gain, all that. So what the students will do is they will connect everything, and then they will ask me, it's not working. That's an issue they have. So what I prefer them doing is you don't connect this, you don't connect this, you don't connect this. You first check whether this is coming correctly, whether this operating point is correct, whether this operating point is correct as you design, this operating point is correct. Like once this is all done, you're sure that what you have designed R1, R2, RC, RE. Once all this is done, then you connect this. Okay, so then what happens after you do this? Then you connect it. Because there could be an issue, like it is actual experimental work, right? In the experimental work, you might connect your capacitor in opposite polarity. This might be plus minus. This should be the way it is supposed to be connected. But if you're using a polarized capacitor and you connect in the opposite direction, it will fail. So that's why you build a small part of the circuit, then you add more and more components. Okay, so once they do that, then they will connect these capacitors and this input to a function generator. They will give a sine wave. Over here also, they will get a sine wave output. It will be phase shifted. 180 will be phase shifted. Okay. So the sine wave part is the AC analysis. This is the AC analysis part. And this fixed voltage, that is this bias point, this average value over here, that is your DC analysis part. Okay. So for it to work well, this amplifier to work well, both your DC analysis should be correct and your AC analysis also is added on top of your DC analysis. Okay. That is the way it is done. So this is, if you see, this is kind of like a system. It doesn't have any switching. But in our case, what do we do is we have for some duration, like this is my entire time period T. Okay. And this is my time period on time dt. And this is the period 1 minus d into t. Okay. So we want to know the overall response of the system from this time to this time. So what do we do? You have your inductor current, which is like this, right? Like this. You have your output voltage, which is rising, falling, etc. So you want to get what the purpose of this technique is, you want to get the average value. You want to get the average value. This is the purpose. You're averaging out this extra ripple. Like this ripple is there, you are averaging out. You assume that the ripple is negligible or small as compared to your average value. Then this hold. Otherwise, this doesn't hold. So you're averaging it out. So in that case, what do? You will do A1 into D plus A2 into 1 minus D. This is your averaged out dynamics into X plus B1 into D plus B2 into 1 minus D into Vm. Okay. This is how you proceed with it. And then afterwards, sorry, this should not be D. It should actually be small d. Mhm. It will be small d. Then the small d, you add the capital D and your D perturbation. So this is your DC component and this is your AC component. Okay. Similarly, in your X also, you have a X steady state DC operating point and your X perturb. For your input also, you have your average input and your input perturb, right? So this is what you will substitute over here, and then you will get a model which will have your DC part and AC part. You separate them out, and you can get the operating point, and you can get the AC frequency response behavior of your system. Okay, this is one way. This is the method known as state space averaging, which is the way I prefer to do. Next is you have what is known as circuit averaging. So in your boost converter over here, this is your inductor. This is your switch, sorry, Q, and this is a complementary one. This is your capacitor. This is your load. Okay. So this part of your circuit, this is the switching part. And this part is which adds a nonlinearity. If you see, this part is linear. This part also is linear. But it is this middle switching part which is adding that nonlinearity. Okay. So what they have is some three-terminal model they have. Like this is the active node, this is the common node, this is the passive node, etc. They have, and they will try to find a model of this, and they'll add it into the system. So they will get, the circuit in an average sense that includes both the DC and the AC component as well. Okay. This is another method. So the advantage with this method is, suppose you add this ESR of the capacitor, or you add the RL of the inductor. You don't have to again repeat the entire steps because those parts are not affected by this Q and Q bar. Those are just the linear part you are modifying. So it becomes easier to deal when you have to make these slight modifications. Okay. But however, nowadays, because of fast computers, everything, you can easily do all this math. You can easily do all this math. You can program it. Yeah, you can do. Okay. So I think it's best we'll start with the sum. That will make it better. Okay. So I will sum for state space averaging. Okay, that's PWM only. So we will consider boost converter. Input is 12 volt, output is 30 volt, R load is 30 ohm. This is the inductance, this is the output capacitance, the switching frequency is 100 kilohertz. So what we have to do is we have to perform state space averaging. Okay, so let us do it. So we have question 1, boost converter. Okay, so what is a boost converter? It is given like this: L, Q, Q bar, C, and your load R. Okay, so let us draw each circuit one by one. So when Q is equal to 1, this is your circuit. This is how your circuit looks like. Okay, this is your current through the inductor. This is the voltage across your capacitor. So this is your current IC. This is your current I naught. And this is your V naught. Okay. So now what is happening is your inductor is being charged, or energy is being stored in the inductor. And in this case, VC is reducing. So VC is being discharged, right? Because your IC in this case is equal to minus I naught. So it is reducing, and your energy or your load is being supplied by the energy stored in the capacitor. Okay, so this is our circuit. So now let us write the differential equations. We know that our Vin is equal to L DIL by dt, because the voltage across the inductor is Vn. So that's why it is Vn equal to L DIL by dt. All right. Now, what is our C dVc by dt? We know C dVc by dt is equal to IC. Now this IC is actually equal to minus I naught, which is actually equal to minus V naught by R. And since there is no ESR, etc., this actually is equal to minus VC upon R. Any confusions in this? You let me know. Okay. So I'm assuming you don't have any things in this. Okay, this is very simple. So let us proceed. So what do we do in state space analysis is, first what I will do is I will write DIL by dt, that is equal to Vn upon L. And my dVc upon dt, this is equal to minus Vc upon Rc. Okay, these are the two equations I got. These are two dynamical equations I've got for the system when it is in circuit A. Now, I will write the state space form. So in state space form, I will consider my state vector x is equal to my inductor current and my capacitor voltage. Okay, don't get confused by advanced terms like state, vector, all that. Like I'm just taking two states, inductor current and capacitor voltage. in this sequence because this is a sequence we generally use. Okay. So now I want to write it in the form x dot is equal to ax plus b into vn. Okay. So what I do is, what is my x dot? It is dil by dt and dvc by dt. If I differentiate, this is like this, right? This is equal to what? This is actually 0 into il plus 0 into vc plus vn upon l, right? And my dvc by dt is equal to 0 into il minus vc upon rc plus 0 into vn, right? So I can write it down as dil by dt and dvc by dt. This is equal to 0, 0, il vc, again 0 il minus 1 by rc plus 1 upon l and 0 v in. Okay. This is your state space representation of your first circuit. Okay. Your state space representation of your first circuit. So this is your A1, this is your B1. This is your X dot, this is your X, and this is your U. Okay. Any queries in this? Or you want me to repeat this? Okay, so we just consider a simple boost converter. Its working is very simple, very easy to understand, but I'm just doing it a little bit slow. If you have any doubts, any queries, you can let me know. Okay, so this is for the circuit case when Q equal to 1. Let us consider case when Q is equal to 0. In that case, what happens? This is my input over here. This is my inductor L. This part is open. This part is closed. This is my C and this is my R. Okay. This is my IL. This is my I naught. This is my IC. And this is my plus minus DC. So in this case, what happens? So now your IC is equal to IL minus I naught. Okay, so in a boost converter, which is more? IL is more or I naught is more? Can anyone tell? We have many people over here. We have Arun is there, Suresh is there, HP is there. HP stands for Hall President or what? We have Divya Sharma is there. Many people are there. So my question is, in a boost converter, is your IL greater than I naught or your I naught is greater than IL?
IL will be greater than I naught
Okay. Why do you think so?
because power remains constant. So input voltage is less than output voltage. So input current will be more than.
Yeah. Correct. Very good. Okay. So your IL is more than your I naught. That means your IC is positive. Okay. If your IC is positive, what does it mean? If your IC is,
Capacitor is charging.
yes, so your capacitor is charging. Okay. Your capacitor is charging. Now, what about the inductor current? Is it charging or discharging? What do you think?
Inductor is transferring energy to load.
Yeah. So the energy stored in the inductor in the previous case, right, is transferred to your load and to your output capacitor as well. Okay, this is the logic. This is how it works. So when you're in your circuit A, your inductor is charging, your output is discharging. And in your circuit B, your inductor is discharging and charging the capacitor. Okay, so it is not like direct, like in a buck converter is different. In a buck converter, that is when your inductor is charging, when your input is connected, you're directly sending power to the output. But in a boost converter, it's not always like that. There are some cases when your output is reducing, but your inductor is charging. And next case is your inductor is reducing, but your output is discharging. Your output is charging. Okay, so it is like that. So that is what leads to what is that, that right half plane zero, which I will talk about later, and a non-minimum phase system. Okay. So now what we will do is we will write a dynamical equation for this. So we have for the inductor L DIL by dt, that is equal to V in. So L DIL by dt is actually your VL, right? So your VL is equal to L DIL by dt, that is equal to V in minus what? Your V output. And your V output in this case is your VC. So this is V in minus VC. So you have to get this equation in terms of the states and in terms of the input. Nothing else. It should be in terms of the states and in terms of your VN. Then only you can write the state space. Okay, so that you have to keep in mind. Now, my IC is equal to C dVC by dt. That is equal to my IL minus I naught. That is, IL is a state, so it is fine. So this is IL minus I naught is what? V naught upon R, which is equal to IL minus VC upon R. Okay, this is how we can write for the capacitor. So now again the same thing we do. We write L DIL by dt is equal to 0 IL minus VC. Okay. Let me grab the L. Let me divide by L. So it is 0 minus VC upon L plus V in upon L. Similarly, dVC upon dt, that is equal to IL upon C. Then minus VC upon RC plus 0 into Vn. Okay. Now we will write it in the state space form. We write it as DIL upon dt, dVC upon dt, that is equal to 0 minus 1 by L, 1 by C, minus 1 upon RC. This is your IL, this is your VC, this is your 1 by L, this is your 0, this is your Vn. Okay, so this is your X dot, this is your A2, this is again your X, this is your B2, and this is the U. Okay, so we got it in this form. Now, I'd like you to notice that your B2 is 1 by L and 0. Your B1 also is 1 by L 0. So in the case of a boost converter, your B1 is equal to B2 and we name it as B. Just simple B, we give it something. Because B is the same for both when it is on and when it is off as well. Okay. So now we have got this. So now what does the question say? We have to perform state space averaging. Okay, let us do state space averaging. So now we have to do state space averaging. So in that, we get the average dynamics, that is equal to D into A1X average plus B1 into Vn, which is also average, plus 1 minus D into A2 average X plus B2 into average Vn. So we are doing averaging over a time period T. Any doubts till this part? So now we have this expression given like this. So now what we want to do is we can combine them. Okay, you can combine them. Let us say we get x dot is equal to d into a1 plus 1 minus d into a2 average x plus d into b1 plus 1 minus b into b2 into average of vn. Now in the case of the boost, what do we have? D into b1, that is we have what? b1 is equal to b2 is equal to b. So db1 plus 1 minus db2 is equal to db plus 1 minus db. So that is actually b. Okay, it makes it simple. This becomes simple for a boost. In a buck, the A is same. So that becomes easier in a buck. So our x dot averaged is actually d into a1 plus 1 minus d into a2 into average of x plus b into average of v. Okay, this we have got. Now what we will do is we will add the perturbations. So what do we do is we replace x, the average x by its steady state DC operating point plus the perturbation in x. The d we replace by the steady state duty plus the perturbation in duty. The v in we replace by the steady state v in plus the perturbation in v input. Okay. When we do that, we will get, this will become x steady state derivative plus x tilde derivative, that is equal to capital D plus D tilde a1 plus 1 minus D perturb a2, that is multiplied by x steady state plus x perturb plus b into v in plus v in perturb. Okay, this is the expression. Now x steady state is a DC value, so its derivative is 0. So what we get is x tilde dot, that is equal to d into a1 plus 1 minus d into a2, right? When we do this, and we have d perturb into a1 minus a2. Okay, that is multiplied by x steady state plus x perturb. Okay, x steady state plus x perturb. And this is what? Plus b into v in plus b into v in perturb. Okay, this is what we have got. Now, what we have to do is we have to expand this. So what we do is we'll expand it. So what do we have? We have our x perturb dot, that is equal to d into a1 plus 1 minus d into a2. This multiplied by x steady state plus d into a1 plus 1 minus d into a2. That is multiplied by x perturb plus d perturb into A1 minus A2 into X steady state plus A1 minus A2 into D perturb into X perturb plus B into V in plus B into V in perturb. Okay, this is what we have got when we expand. Now, which quantity do you think we should neglect? Hmm? Which quantity?
Product of D perturb and X
Yes.
tilde. That
So what we assume is when we are doing this is these perturbations, they are very small. So when we multiply a small quantity by a small quantity, it becomes smaller. Like simple example is if you multiply 0.1 by 0.1, you get 0.01. It becomes even more smaller, right? But if you multiply 2 with 2, you get 4, right? Or you multiply 10 into 10, you get 100. So when in our case, we are considering those perturbations are very small, then negligible as compared to our main DC operating point. So that is why when we are ignoring the product of those perturbations. So what we do is we ignore this. Okay, we have ignored this. Very good. So it's made our life simple. We have ignored something. We don't want to complicate our life. Now, you would have done various maths and control systems, etc. What do we do is we use that. I used to write actually like on comparing the LHS and RHS or on equating the coefficients of the same power, etc. We do that. That is, we are grouping some particular terms together and another particular terms separate because they are different quantities. So what do we do is here we will separate the DC terms from the AC terms. Okay. So what are the DC terms? In our case, DC terms are the ones which have no perturbation. They have no perturbations. And AC terms are the ones which have one perturbation, right? Because the ones which have two perturbations, we are ignoring them. So what are our DC terms? What are our DC terms? This is our DC term, right? And this is our DC term. And DC term over here is 0. DC term over there is 0. What are our AC terms? This is our AC term. 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 So we write it down as 0 plus x tilde dot is equal to d into A1 plus 1 minus d into A2 into x steady state plus b into v in plus d into A1 plus 1 minus d into A2 into x tilde plus A1 minus A2 into x steady state into d tilde plus b into v in perturb, right? So this 0 is equal to d into A1 plus 1 minus d into A2 into x steady state plus b v in. This is your DC model or the DC terms. This one x tilde dot that is equal to d into A1 1 minus d into A2 x tilde plus A1 minus A2 into x steady state into d tilde plus b into v in tilde. This is known as your AC modeling. So what is the difference between the two models? So DC model, will give you your operating point. And your AC model will give you like the frequency response or the behavior of the system for different frequencies. Okay. So how this is your new, this is your A equivalent. This is your B equivalent. And this is your E equivalent. So what do we write it as? We write our average days AC state space as x tilde dot is equal to A equivalent x tilde plus B equivalent D per term plus E equivalent B in per term. If we consider the perturbation of the input voltage as well. Okay. So now we have done all this. Now what do we have to do is we have to find in our case E equivalent is simple. We know E equivalent is equal to B, but we have to find A equivalent. Okay. So can you do D into A1 plus 1 minus D into A2? What does it become? Can anyone do it and tell me? Your A1 actually is 0, 0, 0 minus 1 upon RC. And your A2, let us check A2 is what? 0 minus 1 by L, 1 by C, okay. 0 minus 1 by L, 1 by C, minus 1 upon RC. So what is your A equivalent? Get the expression.
Uh, 0,
Okay.
1 minus
It is 1 minus D by L, then
into that's a minus sign also. Minus of 1 minus D,
okay. Okay,
then 1 minus D into 1 by C,
okay.
minus 1 by RC.
Okay, this is your minus 1 by RC, right? Next, if you will see, sorry, your B equivalent is A1 minus A2 into X steady state. So what is your A1 minus A2? What is your A1 minus A2?
Zero,
A0,
1 by L,
1 by L,
minus 1 by C,
okay,
0.
0, right? Hmm. So now we have to find these for our case. In our case, what do we have? We have to find the coefficients of the matrices. Okay. So we have D into A1 plus 1 minus D into A2. This one. So D into A1 plus 1 minus D into A2 into X steady state plus B into Vn. Okay. D into A1 plus 1 minus D A2 into X steady state plus B into Vn. This is equal to 0. This we need to find for the DC operating point. So we have to find our X steady state. So how will you do that?
multiply by inverse of that matrix A equivalent.
So this actually is your A equivalent, right? So your X steady state is equal to A equivalent inverse minus B into Vn. Okay. So can we, so our A equivalent we know, A equivalent is 0 minus 1 minus D by L, 1 minus D upon C minus 1 upon RC. So we need to find A equivalent inverse. How will we do that?
We can interchange that diagonal A11 with A22, then change the sign of the other two diagonal elements.
Okay, so suppose you have a matrix M, the second order, where M inverse is just dA minus B minus C upon AD minus BC. This is simple shortcut. Okay, so we do the same. So our A equivalent inverse, your D you interchange as he said, so it becomes minus 1 upon RC. Here A is 0, fine. Minus B becomes, so it becomes 1 minus D by L, and this becomes minus 1 minus D by C. But this is not done. You have to multiply further. So 2 A into D is 0, minus B into C, 1 minus D into minus. So it becomes 1 minus D square upon LC. Okay. So now we have to divide all the terms by 1 minus D square by LC. So this becomes equal to minus 1 upon RC divided by 1 minus D square upon LC. Here it is 1 minus D by L, and here it is 1 minus D square by LC. Here it is minus 1 minus D by C, and here it is 1 minus D square by LC, and 0. So our A equivalent inverse becomes equal to C and C get cancelled. So it becomes equal to L upon R 1 minus D square. Here it becomes, again, L and L get cancelled, 1 and this get cancelled. So it becomes C upon 1 minus D, right? And in this case, C and C get cancelled, 1 minus D get cancelled. So it becomes equal to minus L upon 1 minus D, and this is our 0. So these are A equivalent inverse. Any doubts in this?
No, sir.
Okay, so what we do is, now we have to get our X steady state is equal to minus A equivalent inverse into B into VA. This is minus of this L upon R 1 minus D square, C upon 1 minus D, minus L into 1 minus D, 0. And this is 1 by L and 0 into Vn. So this is 2 cross 2, this is 2 cross 1. Resultant should be how much?
Two by one.
Yes. So L into this, so it becomes Vn upon R into 1 minus D square. And over here, it becomes equal to minus Vn upon 1 minus D. There's a mistake. Okay. There's this minus sign over here, minus sign over here. Minus sign will still be over here. Why is this coming like this? Oh, this is minus over here. So this minus is there. This is minus over here. Minus over here. So minus over here as well. So this becomes equal to minus over here. So that is actually equal to V in upon R 1 minus D square and V in upon 1 minus D. So this is your X steady state. Any queries in this?
No, okay, sir. No.
Okay. So your X steady state is what? Your average IL and your average output voltage. So your average IL becomes equal to V in upon R 1 minus D square and your average output voltage is V in upon 1 minus D. So this is the expression for the boost converter, which we know. So that means we have verified that our approach is correct. And this averaging out which we got is also correct. Okay. So in the question, what is our input? V in. V in is 12 volt. V output is 30 volt. So V output is 30, V in is 12. What will be your D? Let me know what is D.
0.6.
0.6. Your D is equal to 0.6. Okay. So now, what is our B equivalent? B equivalent is B equivalent is A1 minus A2 into X steady state, right? So what is A1 minus A2? A1 minus A2 is 0, 1 by L minus 1 by C 0, okay. 0, 1 by L minus 1 by C 0. And what is X steady state is given by this expression. So this is V in upon R 1 minus D square and V in upon 1 minus D. So what is your B equivalent then? This 2 cross 2 into 2 cross 1. So that's why 2 cross 1. So what should be a B equivalent in this case?
V in by L into 1 minus D.
V in by L into 1 minus D. Fine.
Minus V in by RC into 1 minus D square.
Okay, minus V in by RC into 1 minus D square. Okay. So we have B equivalent. We have A equivalent also we got. So over X tilde dot is equal to A equivalent X tilde plus B equivalent D perturb plus B into V in perturb. We found it. So now we have to substitute the values. So V in is 12 volt, L is 3.3 microhenry, and D is 0.6. And what is our R? In our case, R load is 30 ohm. Okay, R load is 30 ohm. And our capacitance is 50 microfarad. So what are these expressions?
Sir, have you wrote some E equivalent in the previous slides?
Yeah. Your E equivalent is actually a B only, right? You see, it becomes B into V in perturb, right? That is actually your E equivalent.
Okay.
Hmm. That's because in a boost converter, your input is always connected. That is why it is actually given by the input matrix only. But this will not be the same for a buck converter or for a non-inverting buck boost also. Hmm. Okay. So can you substitute what are these values? Your R is 30, Vn is 12, D you guys found out is zero point 0.6, L is 3.3 microhenry, and C is 50 microfarad. Okay, so what did you get the first coefficient to be as? Have you guys been able to calculate? We have many people here. Arun is there, he's been answering. Divya is there. Finally, she's able to listen and video. HP also is there. You guys can solve. Let me know what's the values.
Sir, B equivalent, I got 9.09 into 10 raised to 6.
Okay. And the other one?
And minus 0.05 into 10 power 6.
10 to the power 6. Okay. What about others? HP and Divya are very quiet, very shy. It's fine. Even if you make a mistake, you won't lose marks. It depends on your assignments and your exam. Okay. Okay, B equivalent you have got. Now we have to find A equivalent. What will be those values? A equivalent. Let me write it separately. Your A equivalent is 0, 1 minus D by L, minus 1 minus D by C, minus 1 upon RC. Let me just check again. Okay. Okay. This is a minus, this is a plus. So what will be the value of this? Let me know.
Zero.
Okay. 0.
Minus 1.212
Okay.
into 10 power 5.
All right.
0.08 into 10 power 5.
0.08 into 10 to the power 5. Next.
Minus 0.0067 into 10 power 5.
Okay. If we make it into 10 to the power 6 or 10 to the power 3, because that's how usually it will come in the question. Okay.
Okay, okay, sir.
Yeah. And what is the E equivalent? That is equal to B. That is equal to 1 by L and 0. So what is this value? What is 1 by L?
3.03 into 10 power 5. So
Okay, okay.
0.303 into 10 power 6.
6. Correct, correct. Okay. So this is good. Mhm. And yeah. So congratulations, we have finished this very hard question. And in this case, we have considered the perturbation of the input voltage as well. This is done. We'll go to the next question. Can you tell me what is right, what is wrong in this?
All are correct.
All are correct. Okay. Mhm. Right. What about our HP, all precedent? Mhm. So what are the different inputs which we apply to our plant, to our DC-DC converter?
Input is DC voltage.
Okay. That is the even our load, our actual load current which we draw, that also is kind of like an input in when you do the modeling everything. Because the load is something external, right? So how much the load draws current, that also changes your behavior of your plant. So we want to analyze the dynamics of the plant. In that, we want to realize like how fast our plant can respond. So those things, that is your your dynamics of your plant. They dependent on your L value, C value, your R, your duty, etc. It depends on this. So sometimes what we see is like as we had also told, a light load control strategy. High load we prefer PWM. Light load we try to do variable frequency, etc. Different things are there. What is the dynamic? How fast? Like depend if your L is small, then your current can change abruptly, which is required for load transient. And if your C is small, then your output can change fast. It can change quicker. But if your C is large, your output will change slowly. So we cannot keep our C also to be very small because then our ripple will increase, which is not desirable. So the C usually is very high. L we take it a little bit smaller such that we can change the current faster at a higher rate. Okay. So then we want to analyze the dynamics of the plant. We want to predict the behavior of the system for different inputs. So when we change the input, we will see how it will respond for them. We assess the stability and performance of the system. Like stability is something which is really important, right? We want our system to be stable. We want it to behave as we want it to behave. Like don't want it to have lots of overshoot. We don't want it to work very slowly. We want it to work decently at a fast enough rate, and we want it also to be stable. Okay, and we also design controllers for achieving the desired performance. So normally your system or your plant is not going to give you the response to the speed which you want. Suppose you want to increase the speed, or suppose you want to make it more stable. You want to increase the phase margin or the gain margin or something, you add a controller. So when you add a controller, you need to have a model of the plant to show how the plant behaves, how it actually behaves. Okay. So for that, all we do modeling. Okay. And modeling takes a lot of time, takes a lot of patience as well, right? But it's very important. So any doubts in this part? Any queries or anything?
No, sir.
Okay. Good. So we'll go to the next question. So what is the purpose of DC circuit averaging? What do you think?
Option A.
Okay. What about the others? They all are false or they are true?
Second option is not correct. DC analysis is not sufficient.
Why? Why? This you want it to work in DC, right?
But for small signal variations, we need this transfer function analysis.
Okay, okay, yes, correct, correct, yes. Then what about C?
Uh, loss calculations, we can do DC analysis. That is also correct.
Okay, okay. Then last part.
Volt second balance and charge balance are valid in a steady state. So that is also correct.
Okay, okay. Yeah, yeah. Very good. So yeah, as we had done over here, right? We had found our X steady state like this. This X steady state, we did all this inversion, everything, and we got our steady state given by this expression. But this very same expression can also be got if we do inductor, volt balance, capacitor charge balance. So you'll get the same expression. Okay. But I'd like to point out that in this analysis which we have done, we have not included any of the switch on resistance, the inductor DCR. We have not included the ESR of the capacitor. All those things we have not included. So those things we must include. Okay. I'd like to do the circuit averaging, state space averaging for a realistic boost converter. Okay. So what we will do is we have our, this is my input, right? This is my L, this is the Q, this is the R on, right? This is your Q bar, this is your R on. Similarly, I forgot, you will have what is known as a, Mhm. You'll have a DCR of the inductor. This is your input. Okay. This is your R on. This is your RC. This is your C. And this is your load resistance R load. Okay. So how do I represent this? Like, how do I do it. So what I do is, again, let's consider case Q equal to 1. So my circuit reduces to what? Plus minus Bn. RL is still there. L is there. This turns out to be R on, right? Here, similarly, you have RC, you have C, this your R load, this is your IC, this is your I output, this is 0. So here is the thing when it becomes more realistic, more practical. So we have the LdIL by dt, this equal to Vn minus IL into RL plus R on. And our C dVC by dt, this is this Vc, okay? And this is my V out. So my C dVC by dt, this is equal to IC, that is equal to your minus I output, right? So your C dVC by dt is equal to minus V output by R load. Or let us just say R. Why to make it complicated? So this is a minus V output by R. But we cannot use this because V output is not a state. We want it in terms of the state. So what we know, your V output is what? VC plus IC into RC. This is your V output. This is your VC. So this is your V output is VC plus what is your IC? Your IC is nothing but minus I naught RC. Right? So your V output is VC minus I output is V output by R. V output by RC. So your V output, we take it this side. So it becomes 1 plus RC by R. This is equal to VC. So your V output is what? R plus RC upon R is equal to VC. So V output is equal to R upon R plus RC into VC. This we denote as alpha VC, where our alpha is equal to R upon R plus RC. This is our alpha. This you might have come across in the expressions, but you do not realize why it would have come. So I'm just explaining to you. So now, what do we know? V output is VC plus ICR. So your V output is equal to alpha VC. So we can write C dVC by dt, which is actually your minus V out by R. This is actually your minus alpha VC upon R, right? So we are writing it in terms of the states because we are representing in terms of the state space. So these differential or these dynamical equations should be in respect to the states and the inputs. Your V output is an output, but you should write it in terms of the states. Okay. So this is done. So for Q equal to 1, your DIL by dt, that is Vn minus IL into RL plus R on, here L by L, and your dVC by dt, that is equal to minus alpha VC upon RC. This for Q equal to 1, and your V output in this case also is equal to alpha VC. So this expression also you got. Now, for Q equal to 0, we need to find. Q equal to 0 is what? You have your Vn over here. You have your L, RL, R on, RC, C, R. Okay? This is your IL, this is your I naught, this is your IC, this is again your IL. So in this case, let's start with finding what is your, this is your V output, this is your VC. So again, your V output is actually equal to VC plus IC into RC. Oh, I made a mistake here. This is your IC, this is your I naught, right? Your V output is equal to VC plus, what is your IC? IC is equal to IL minus I naught into RC. So your V output is equal to VC plus IL RC minus I naught into RC. That is VC plus IL RC minus V output by R into RC. So the V output into 1 plus RC upon R, that is equal to VC plus IL RC. So actually this is V output by alpha, the VC plus IL RC. So your V output becomes equal to alpha VC plus alpha into IL RC. So because of this RC, this culprit comes. This creates this alpha, we have to rederive. When this RC is not there, my V output is equal to VC. So it becomes easy and simple. But when this RC comes, these things have to be taken into account. So this is what makes it difficult. Similarly, we can write our L dIL by dt. That is this voltage. We are taking the KVL of this. Sorry, KVL of this. So this V in minus L dIL by dt minus IL into RL plus R1 minus V output. So your L dIL by dt is V in minus IL into RL plus R0 minus V output. But this equation will not suffice because V output is not a state or an input. So that's why we have written it in terms of states. So your L dIL by dt, in this case, it is Vn minus IL into RL plus R1 minus alpha Vc minus IL alpha into IL RC. So your L dIL by dt, that is equal to Vn minus IL into RL plus R1 plus alpha into RC minus alpha into VC. Okay? This is the expression. Similarly, your C dVC by dt, that is equal to your IL minus I output, that is equal to your IL minus V output by R, right? That C dVC by dt is equal to IL minus, what is your V output? V output is alpha VC plus alpha IL RC. So that is equal to alpha VC plus alpha into IL RC upon R. So your C dVC by dt is equal to IL into 1 minus alpha RC upon R minus alpha VC upon R. So now C dVC by dt, it is equal to IL 1 minus, what is alpha? Alpha is R upon R plus RC into RC by R minus alpha VC upon R. So this R and R gets cancelled. So it becomes C dVC by dt is equal to IL into R plus RC minus RC upon R plus RC minus alpha VC upon R. So C dVC by dt, it is equal to IL into R upon R plus RC minus alpha VC upon R. So this is actually equal to your IL alpha minus alpha VC upon R. Okay. So we can write for Q equal to 0, dIL by dt, that is equal to minus IL into RL plus R1. What is it? Wait a minute. Sorry. RL plus R1 plus alpha RC plus alpha RC by L minus alpha VC by L plus Vn upon L, and our dVC by dt, that is equal to IL into alpha by C minus alpha VC upon RC plus 0. This is done. So any doubts still here?
No, sir.
Okay. So let me try getting this. Balance. So there is this symbolic math toolbox. This sir is not shown to you guys, but it's something which is like something nice, which I feel. So you can have what is known as your V underscore I underscore N. Okay. You have your R underscore L, R underscore R. Let us check how it looks. Mhm. So it will show like this. Okay. And the advantage with this is you can copy it as a latex, right? And we usually use MATLAB in our lab. So just hold on. So when you will write papers and reports, you will use latex. So you'll have to write these equations. So this is your VN. So this is your VN which you get. So this is a way you can write expressions, everything, right? Your RL also will look like this. You will see. This is your RL, this is your R on. And when you will write equations in these papers, everything, this is your V. Then in the subscript, you have written IN. Okay, this is fine. You have your R. In the subscript, you have L. L is just a single thing, single letter. That's why L you will see is italicized. But in the case of R on, you have R and ON, they are two letters. That's why they are not italicized. Similarly, in the case of VN. So this is the standard format which is used while writing mathematical equations, etc., in papers, everything. And this symbolic math tool works. It follows that. Okay, it follows that. So it makes it simple and easy, right? So I thought of using this. So we have defined RL, R1. Similarly, we have our RC for our ASR of the capacitor. What is left? We have our inductance L. We have our capacitance C. Then we have our load resistance R. So these are our three variables which we have. These are the variables which we have. Now, we will write our A1 matrix. Okay, A1 matrix. So in the case of what we have derived, A1 is the matrix when Q equal to 1. So A1 matrix is what? RL plus R1 upon L and 0. And then 0 and minus alpha upon R. Okay, so we have to have one more thing. We have to have what is known as alpha as. Okay. So the A1 matrix is actually equal to minus RL plus R1 upon L, which is minus of R underscore L plus R underscore R by L. Okay, then since it's a matrix and it's in the same row, we do by comma. Then over here, it is 0. Okay, it is next is 0. Next we go to the next row. dVc by dt is not dependent on IL. So again, that is 0. So this is 0. This is minus alpha by v square. Alpha by R into C. Okay, this is done. Let us run it so that we will know. Why it's not coming? Okay. So this minus sign should not be here. Okay. So this is coming in the mathematical form. Okay, and this again you can copy into latex and you can run it. Let us say how to copy. Copy as latex, paste over here, and you have got the equation. Okay, this is very useful. Right? So this is your A1. Okay, this is your A1. What is your B matrix? B matrix is 1 by L 0. So Arun, actually you would have seen this in the previous time, right?
Sir, in that state space control course, you have taught this.
Okay, then it's easy for you. Okay. Um, so this A1 and B we have got. A2 will be equal to, it is our A2. In this case, it is RL R1 plus alpha RC. So it is minus of RL plus R1 plus alpha into RC by L, comma, minus alpha by L, minus alpha by L, then alpha by C, comma, minus alpha by R, minus alpha by R into C. So let me check this is my A2 matrix. Okay, this is my A2 matrix, which I've got. B already I have. Now I want to write my C1. My C1 matrix actually is, C1 is my output voltage. So in the first case, my C1 is just alpha into VC. So C1 is equal to 0, comma, alpha. In this case, okay, while in this case, my C2 is equal to second mode, sorry, C2 is equal to alpha VC plus alpha RC. So it is alpha, comma, alpha into RC. Okay, let us check them. So we got C1, C2, A1, A2, all of them are fine. So let me parameterize them. Let me comment them. Now we'll take symbols D, capital D, etc. So let us say our A average. Okay, that is our D into A1 plus 1 minus D, 1 minus D into A2. So let us run that. So this is our overall averaged expression, which we have got. So now, what is our, we have done some math. In our math, what we had seen is our A equivalent is actually D into A1 plus 1 minus D into A2. Okay. So let us do that. So our A equivalent is equal to D into A1 plus 1 minus D into A2. So now just D, we are replacing by capital D. Capital D is our steady state duty. So this is our A equivalent. Okay. What is our B equivalent? B equivalent. What is our B equivalent? Okay, our steady state also we can get. Steady state operating point we can get. X steady state is minus inverse of A equivalent into B into Vn. So let us run this and see. So Vn is what have we defined it as? V underscore A. Okay. So this is our X steady state. So this has all the parasitics, all that is included in that. Okay, this is our X steady state. So this is our steady state operating point. Now they have got A equivalent, we have to get B equivalent. What is B equivalent? B equivalent is A1 minus A2 into X steady state. Okay. So B equivalent is equal to A1 minus A2 into X steady state. Let me run this. So this is our B equivalent expression. So any queries to this?
No, sir.
Mhm. Okay, so like have you used this afterwards, this symbolic math toolbox in your work?
Sir, this copying to LaTeX, this I am seeing for the first time. I have not seen that.
Oh, okay, okay. That's because I actually wanted to find a tool which can, do the math so that it can be coded. I don't need to manually do it. So, like the simple maths, it's able to do, but the complicated maths, it's finding it difficult actually. That I've seen. Like it can also do differentiation. Suppose this A average is there, we'll do differentiation of A average with respect to D. That is one. So it will differentiate with respect to D. That's differentiated with respect to D. So what is our A average? This is our A average. It's differentiated with respect to D. Okay. Can do that also. Doing it well. Hmm. Okay. If I do okay. Acha. So what were we supposed to do was B equivalent. We got E equivalent also is E equivalent is B, so it is fine. We can substitute A equivalent ideal. Substitute A equivalent old. Okay. Parasitics. What are the parasitics? That is your RL, R on, your RC. These are parasitics. And your ideal case, we want it to be 0, 0, 0. Right? So our old is the parasitics. And this is the ideal. So let us see what it comes. Okay, comes like this. So this is the one which we got, but alpha is also there. And alpha in the case of that is alpha in the case of ideal, it is 1. Okay. So if we run it, we get it like this. So this is what we had got, right? In the ideal case.
Yes, sir. But that 1 minus D into 1 minus, that step we have to manually do.
Yeah, it was, it's not able to do that. Simplify. It did it. Create a simplified expression, show the code. Achha. This is what I have to use. So, something like this. Yeah. B for this. So I just have to do simplify it. I do simplify it. Yeah. It is doing of the math. Okay, it has done it. So this for the ideal case, it is matching. So this is good in that case. Similarly, what did we do in the ideal case? A equivalent we got, B equivalent also we got, right? So B equivalent we have to again substitute. Let us check. So B equivalent in the ideal case is simplified. Just copy it. B equivalent parasitics ideal. Okay, let us check what it comes. Okay, this is what it has come. Mm, This is correct or there is some mistake here?
Uh, uh, Correct, I think so. I don't remember the exact expression.
Let's check. B equivalent which we got. We got V upon L into 1 minus D. Okay, that is. Okay. Just they taken D outside. So it is minus the same. And then over here, B equivalent is minus V upon RC 1 minus D square. So minus V upon RC 1 minus D square. Okay. I think we should put a constraint. Assume B less than 1. Just check whether it works with that. Better. There should be some case. I have done it before. Like you can say that B is less than 1. I think it will do better. Okay, so they are more or less coming the same. Hmm. That's true. Okay. So I think these things also you can explore. It could be useful for you later on. And do you have any other queries or
But
stuff? Okay.
sir, at this step, if we want to substitute, say d equal to 0.6 as in that problem, what is the command? We have to simply write d equal to 0.6 or
Yeah. You have to do A equivalent. Let us say the value is equal to substitute A equivalent IT. D you are substituting with 0.5, 0.6. Okay, let us run it now. You get it. Now you have to substitute value of L, C, and R. So
okay, sir.
let us say our what you say our passives. Okay, those were L, C, and R, and our passives value is L was 3.3 E minus 6 microhenry, C was 50 E minus 6, R was 30 ohm. Okay, and let us add D also over here to make it simple. 0.6. Okay, so we have to just put passives and passives value. Let us run it. So is this the value you got? 8,000 did you get?
0.08 into 10 raised to 5. I think same.
Okay. So there should be something I know what this code is. BPA. Right. Just check this. Should work. Is this what you got?
Yes, sir. Yes.
Okay. So this is actually very useful. So we can do B equivalent value also. This will be Current ID, substitute value, we get in the score equal to ID. Run it again. Ah, okay, we have to substitute V in also. Okay. V equal to underscore val, substitute underscore val, comma, V underscore N, comma, 12. 12, right?
Yes, sir. 12 volt.
So this is the value you get. Think this is also what you got, right? Need is minus 5,000 point. There's some round off is there, like some rounding error is there, but that can be neglected actually. And when your exam, you will be told to find only till the second digit or third digit. So it's not an issue there in the exam. It's there. Then any other queries or some doubts which you have from what sir has taught?
No, sir.
So how's your work and all going on?
Um, trying to complete watching these videos. Another one course is also there.
Which course? Which course?
So, power electronics for wide bandgap devices.
Oh, it's taught by whom?
It is Dr. Maumida Das in IIT Mandi.
Acha, acha. Oh. So what and all they are teaching in that?
They are teaching about theoretic. It is mainly theoretical course. No, not many numericals are there. Mainly about
Okay, okay.
silicon carbide and gallium nitride.
Okay, okay, okay.
Their protection and layout, heat sink, all those things.
Oh, okay, okay, okay. So they are using any layout software or something?
No, it was mainly theory only,
Okay.
not any hands-on.
Sure. And there's no like loss calculation, everything like double pulse test or something?
Yes, yes, double pulse test was there in week 2.
Okay. Sure. Like what are they at? They have like the gate driver circuit for GaN, gate driver circuit for silicon
Yeah.
carbide.
Yes,
Sure.
yes, yes, yes.
Mm-hmm. And heat sink design probably based on the thermal resistance, all that they get. And what?
Problems were not there, but
Okay.
heatsink theoretical aspects about heatsink design was discussed in week 4 or 5. Week 4, I think.
Sure, sure. But probably you're finding that course much easier than this course, right?
That is relatively easy compared to this one.
Yeah. Yeah, this course is actually very difficult. It's very difficult. Control systems is always difficult, I feel. Yeah.
Yes, yes.
Yes. Okay, we can continue. Whatever doubts next week also we can meet. And
Okay,
yeah, we can continue. Okay. Thank you for joining.
okay,
Yeah.
sir. Thank you.
Good night.